All right, let's do it. Let's do some maths. A stone, 16 grams, is acted on by a force 0.6 newtons. What will be its acceleration? So we know our formula here. Force equals mass times acceleration. Now, force needs to be measured in newtons, so 0.6 newtons. Mass needs to be measured in kilograms, so 0.016 kilograms. And acceleration is the thing I don't know. Solve for A. That means this stone's acceleration is going to be 37.5 meters per second squared. Now, it's important to note that this stone might have been standing still. If this stone was standing still, this was our acceleration, 37.5 meters per second squared. This stone also just might have been rolling along at a constant velocity. If it was, this is going to be our acceleration. We're giving it an extra push along. If we were sort of standing in front of it, it was rolling towards us, we're pushing the other way, but that force should have been negative, right? Because force is a vector. Alright, so that is a good use of F equals ma. Second example here, an object, 150 grams, loses speed from 26 meters per second to 24 meters per second over 35 meters. Find the uniform force acting on the object. Alright, so we know eventually we're going to end up at force equals mass times acceleration. We want to know the uniform force acting on it. We know the mass, 0.15. We don't know the acceleration. But we can find the acceleration because we know that it decelerated from 26 meters per second to 24 meters per second over the space of 35 meters. So acceleration's our problem, but we're given initial conditions of velocity and displacement. So we can use acceleration equals dv dx v, and we can start working from here. Now, we know that acceleration here, uniform force, there's uniform deceleration here, which means that acceleration is going to be a constant value. I can use separation of variables here and treat acceleration as a function of x. So I'll get a dx and v dv. And integrate both sides. Now, integrating this side's pretty easy. The integral of v is v squared on 2 plus c. Be careful here. This is a constant. It's like the number 5 or the number 12. So the integral of that is going to be ax and then a plus c. But I've got a plus c here, so I don't need to worry about it. What I have near now looks incomplete, but it's enough stuff. We've got everything we need because we've got a relationship ax equals v squared on 2 plus c. And we know some initial stuff. We can say that velocity equals 26 when displacement equals 0. Now, I'm being a bit sneaky with this displacement equal to 0. We don't know where this object was when it started decelerating, but treating the place where it started decelerating as being displacement 0 allows us to do this. So when we sub that into our equation, we get this constant value is equal to negative 26 squared on 2. And we can sub this value back into this equation right here. So we're one step along. We've got ax equals v squared on 2 minus 26 squared on 2. That a I can find now because I've got additional information. Not only do I know that v equals 26 when x equals 0, I know that v equals 24 when x equals 35. So of course I can take that information and sub it back into that equation. So there it is, I've put 35 and 24 into my equation. Now this whole thing here is negative 50 divided by 35, and we get an acceleration equal to negative 10 over 7. Negative's good because it's decelerating from 26 to 24. We're about done here because remember what we were trying to find? The uniform force acting on the object. If we've got a mass and if we have an acceleration, we definitely know the force. Force equals mass times acceleration, which is negative 3 on 14 newtons. Now remember, force is directional, and so we should expect this force to be a negative value because it's slowing this object down. It's working in the opposite direction to the object. So we'll just do a quick little part B here. How much further will the object travel if this force keeps acting on it? Alright, so we know that it's decelerating at this rate. we know that we have an equation in terms of the uniform acceleration and displacement and velocity. So how much further will the object travel? The object stops traveling when its velocity is equal to 0. So let's write this equation out and let v equal 0. So this is our equation that links displacement and velocity. Velocity is equal to 0, and the displacement would be an additional, the displacement will be 236.6 meters. Is that our answer? It says how much further will the object travel. We know that it's already decelerated over 35 meters. This function, remember, starts at displacement 0 before this thing happened. So how much further will the object travel? The answer will be this number, 236.6, minus the amount that it's already covered, 30. That's 201.6 meters. How much further will the object travel? That amount. Alright, this question, we're looking at a real change of pace here. This one's going to be relatively straightforward. Three forces, force 1, force 2, force 3, act on a 2 kilogram object. Force 1 is this, force 2 is this, and acceleration is this. Find force 3. Alright, so let's take a look at what this picture looks like first of all. We have a particle here. There's a force acting on it, 2I minus 3J. 2I minus 3J, 1, 2, 3. A force that looks like that. There's another force acting on it, 4I plus 2J, 1, 2, 3, 4, 1, 2. A force that looks a little bit like that. Its acceleration is 4I meters per second squared. So it's accelerating in this direction, right? Now there's some other third force acting upon it, and it's our job to figure out what that third force is. Now, again, we've got a mass here, we've got an acceleration here, and we've got forces. So we've got our force equals mass times acceleration thing here. Now, in this case, it's not a single force acting on this object, it's three forces acting on it. And all of those forces acting on it are what make up this mass times acceleration. So we've got force 1 plus force 2 plus force 3 is equal to the mass of the object times the acceleration of the object. Now, we know most of that stuff, we just don't know what force 3 is. So we knew force 1, we knew force 2, we don't know what force 3 is, but we know that those forces combined are going to be equal to the mass times the acceleration. And the acceleration has a direction, 4I. Okay, so let's group these together and do this multiplication. And from here you should see it's pretty straightforward. 6I minus j plus force 3, which could be an I and a j component, is equal to 8I. Let's rearrange so we're just getting force 3. Easy peasy. Force 3 is equal to 2I plus j. Let's take a look at our picture here. 2I plus j, about there. And these three forces together are pushing this object in this direction. And you could double check that to make sure that everything's adding up correctly, but that's what we're looking at with these three forces and this force equals mass times acceleration idea. Alright, those three examples were wide-ranging. There's some different ideas in there, but it really is the amalgamation of a lot of things that you've already learned.